Anyways,
Okay.
Michal Eckstein from Krakow with Jagiellonian is given the talk.
Okay. Thank you very much. Thanks to the organizers for inviting me to this very nice event. Let me start with an advertisement. You know, it's like on YouTube. You have to first watch the ad to get to the content.
You can skip that.
No, I cannot. I cannot.
After 5 seconds.
Okay. Okay, so there will be a very nice event going on in Impan, Warsaw, this autumn. And that would be a Simon's semester organized by very famous people, Paul Baum, Alan Carey, Piotr Hajac, and Tomek Maszczyk. So 2 of them are here. I leave you guessing which one. So you can approach them, you can ask questions, and they will tell you everything. And apparently what I learned is that they have a lot of money. Yes, but especially for young people. So if you're a PhD student or a young postdoc, you want to apply, then you better do it, and you better do it quickly. Okay, so the program, there are very many interesting events. So it starts with the master classes, right? And there will be 4 topics, which are exactly the topics of the conferences that will follow. Something on cyclic homology, noncommutative index theory, topological quantum groups and Hopf algebras, structure and classification of C-star algebras. Okay, so there will be master classes. Then there will be some introductory workshops, right? Courses. True, yes, with courses, it says here explicitly. And then there will be the regular conferences, one just after another. So a lot of interesting things. So you can either ask Piotr for more details or Tomek, or you can just Google it up. Okay, so let's get to business. So as we all learned from this workshop, noncommutative geometry a la Kohn is a very convenient tool to generate particle physics models. Well, it has a lot of pros. It puts some constraints on admissible models. So you get some constraints. You cannot just have any particle physics model. It's quite heavily constrained. The gravity is included into the game, so that's good. And you do have some concrete predictions, which is nice. You can predict masses, couplings, whatever. But there are also some cons of the Kohn's approach. Namely that the signature is wrong. Everything is Euclidean. We want our word to be Lorentzian. As you have seen, there is some step and some tendency towards this, but it's far from being settled. And the second thing is that you're having classical fields, right? Whereas, of course, at the end, you want a quantum field theory to get cross sections and so on. But let me ask the following question. Is noncommutative geometry only a tool to generate these models? Now, I would say that no. That's my belief. That's my faith. Well, probably most of you would agree with me that that's a common viewpoint. It also appeared, for instance, in Myri's talk, that what you really look at is almost commutative geometry, but you think that this is an approximation of something truly non-commutative that sits down there and waits to be discovered. But if you take this point seriously and you want to think about physical principles that lie behind it, then you follow into conceptual problems. You have to redefine many of the notions you were accustomed to, like the space and time, the space-time interaction, evolution, symmetry. All that needs to be rethought, right? Because what it means really that the space-time is non-commutative. So what is a non-commutative space-time otherwise? Then a second important question is, what are the actual empirical signatures of the non-commutative picture of the work? If this is a true picture, it should give some consequences. Of course, you can get the particle physics models, but I have the impression that's not all. I mean, you need something to really say that, okay, that's the proper description of the proper model of the world. Okay, so during my talk, I will try to convince you that you can get here, but you need to treat at least this field seriously, probably this one as well. Okay, so let me first just briefly flash through the usual approach of con. Well, you all know that, but just to see where we are. Okay, so you have a spectral triple, which, as you might easily guess, consists of 3 objects. You have an algebra, which is some dense star subalgebra of a C-star algebra. Typically, it will be unital, which corresponds to the compactness of your underlying space. Then you have a Hilbert space on which your algebra is faithfully represented in terms of bounded operators. And then you have your Dirac operator, which is densely defined, self-adjoint. It should have a compact resolvent and bounded commutators with all elements of A. Okay, so that's the bulk, the core of the definition, right? Then you can have additional structure. You can have reality structure. You can have chirality, so odd, even spectral triples. You can put more conditions, more technical, like some smoothness conditions, p-summability, or whatever. If you're after a reconstruction theorem, you need to consider these. Then if you want to constrain your models, you have to assume something else, like, for instance, the first order condition, whatever else you want. Okay, so that's how it is. If you do so, you put all these technical assumptions, you can arrive at the reconstruction theorem, which says that for every commutative spectral triple, so spectral triple fulfilling all of the possible axioms with a commutative algebra, there exists a smooth compact spin-Riemannian manifold, which is described in the following way, as you all know. Now, what else you can do? You can take your favorite matrix algebra, represented on a Hilbert space, and take a matrix acting on this Hilbert space, and you call it, as long as it's self-adjoint, you call it a Dirac operator. Okay, and here it is. You have your finite spectral triple. Then what you do, you tensor it, and you obtain an almost commutative geometry. So you have an algebra, you have a Hilbert space, and you have, again, a tensor Dirac operator. And at the level of applications, the algebra tells you roughly about the gauge group of the model. This encodes the fundamental fermionic fields. And the Dirac operator tells you about the dynamics and also the masses and mixing angles, things like that. Okay, so once you did that, you choose your favorite matrix algebra, which is, of course, this one. Find a suitable Hilbert space representation, and even more suitable Dirac operator. Then you compute the action, fermionic action plus the spectral action, and what you get is just some Lagrangian density integrated over your manifold. And this is at this point where you actually forget about non-commutative geometry. You forget where it all came from. You just take this for granted. And then what you do? Well, you do the usual things. You Wick-rotate, quantize, do the RG flow, compute the cross-sections, and so on and so on. And what you get at the end, well, that's not bad at all. I mean, you recover the standard model, can predict new fields, masses of particles, things like that, and you can even address some cosmological questions because you have gravity included into the game. So that's not bad, I would say. But still, I feel a bit bothered by the fact that this is at this point where you actually see that, okay, well, I have an action, and now I just do the usual thing. So I think there is more about non-commutative geometry. And okay, so let me clear the dust from one of the corners of non-commutative geometry that is almost forgotten by now. That's at least my impression, namely the Const distance formula. So recall that if you have a C-star algebra, or anything dense in it, you can consider states on it. States are just positive linear functionals of norm 1, and they form a nice closed convex set for a weak star topology. And since it is a convex set, it means that it has extremal points, and these extremal points, well, you call them pure states. Okay? And once you have a space of states, and you have a corresponding spectral triple with a nice Dirac operator, you can write down this formula. That's the Const distance formula. And it tells you that you can actually measure distances between states in the algebra. So how do you do that? Well, you take elements of your algebra, you pick up the ones which satisfy this condition. So you take commutator with Dirac, compute the norm. If it's bounded by 1, then it's admissible. Then you take a supremum over all that of this quantity, and here is your distance. Well, actually, it's a pseudo distance because it can be infinite, and it will certain cases, actually. Okay, so why this formula is so nice? Well, of course, you recover the usual things. If you have just your C-star algebra of continuous functions vanishing at infinity over a manifold, so you have a spectral triple associated. You look at the pure states. Well, Gelfand-Naimark will tell you that your pure states just correspond to the points of your manifold. Then you look at the full space of states, so mixed states. You will get probability measures. That's Riesz representation here, right? Okay, so of course, points, these delta functionals are special examples of probability measures on your space. And if you now compute this formula for pure states, which are related to a point P and a point Q of your manifold, you just recover the usual geodesic distance between these points. And if you try to do so for probability measures, well, what you recover is the first Wasserstein distance. That's something Francesco D'Andrea and Pier Martinetti, they showed. So that's a very nice link, very nice link with optimal transport theory. Okay, but of course the whole idea of NCG is that you can do more than just commutative, than just rephrasing the commutative stuff. So what you can do, for instance, is to look at the finite spaces, which from the spectral point of view, they are zero-dimensional. Because, well, your algebra is finite, your Hilbert space is finite, your Dirac operator is just a matrix, so everything is zero-summable, right? But these guys do have some internal space. And one of the viewpoints on this internal space is that you can look at it via the space of states. Well, that's how you can define it. For instance, if you take just the algebra of matrices, complex matrices, then all of the pure states are vector states, and actually you will get a CPn minus 1. And this is something people from quantum information theory, well, they call it qubits or n qubits. In particular, if n is 2, you just have a qubit here. And if you look at mixed states, well, you will just discover density matrices. So that's just the same thing. These people are using. Now, if you have direct sums of algebras, you will have disjoint sums of pure states. So in this way, you can have some. That was what's called two-pointed space, four-pointed space, and so on and so on. And there's an important result by Caddison saying that if at least one of the C-star algebras is commutative, then, and of course they are sufficiently nice, nuclear and so on, so that this is well defined, then you have this equality. So all of the pure states on your algebra are actually separable. It means that they are just tensor products. So the spaces of pure states will just be a direct product of these guys, if at least one is commutative. So that's, of course, the situation in the almost commutative setting, right? And there were some works on the Kahn's distance formula in finite spaces, and just a tiny part by Pierre in almost commutative things. But, well, I might be wrong, but I think that I might have pretty much listed most of the people who ever did something about it. Probably not. Okay. There are more, for sure. But anyway, what I want to stress is that this is not really a popular thing. It's even less popular than Lorentzian non-commutative geometry, I have the feeling. And I think that's bad, because this is where new results can actually come. Because this is something that really goes beyond this usual approach of saying that, okay, we have an action and then we quantize it in the usual way. This is something that sits in the structure of the non-commutative space. So that's maybe where you have to look at. Now, okay, but if you want to draw some physics out of it, we'll try to convince you. You need to consider the Lorentzian aspects seriously. Now, I'm lucky enough to have Nadir just before me explaining what's a pseudo-Riemannian spectral triple and to get all of the nasty questions. And then I have Kuhn to back me up just after the lunch. Therefore, I can allow myself not to focus too much on the whole machinery of pseudo-Riemannian spectral triples. I will just give you a, say, minimal definition. So, again, some kind of core, like this core of the Kahn's definition. that I really need for the things to work. But otherwise, well. So the essential thing is that there is need for indefinite inner products. And for that, well, the idea is to go to Krein spaces. That seems to be a good idea, and this is common for all of the approaches to NCG. Now, it's very much work in progress. For the moment, probably there are more definitions than people working on it, which is kind of a drawback. But anyway, I put here a kind of minimal definition, so the things that are included in all of these approaches. And then you can do more. But what I need is really that. So you need a dense star subalgebra of a C-star algebra, presumably a pre-C-star algebra if you want, which is represented on the Krein space, which means represented on the associated Hilbert space. And you need a Dirac operator, so again something densely defined, Krein symmetric, so symmetric with respect to the indefinite inner product, and such that this commutator extends to a bounded operator for all A. That's what I need. I don't care about compact resolvent, reality structure, nothing like this. This is what I need. Okay. Now, once we have that, I do need to do one technical thing, namely I need to choose a unitization of my algebra. Because since I want to do some Lorentzian geometry, well, Lorentzian manifolds, typically they are not compact. I mean, if they are compact, then they are pathological in the sense that they always have closed causal curves. So I want the things to be non-compact. If I want the things non-compact, I need non-unital algebras. So at some point, I need a unitization. I treat it merely as a technicality. There might be some deeper points about that, but okay, let me explain to the definition first. So what we proposed with Nicolas is to define the following structure. So you take your favorite unitization, and you take all of the elements from this algebra, which form a cone. So you take self-adjoint elements. If you add two elements, you're still in the cone. If you multiply by a positive scalar, you're still in the cone. And your identity is in the cone. So for this, I need unitization, obviously. And now, I need another condition. So if I take any vector from my Krein space, and I compute this product, it should be negative definite. All right? And that's, if you look at this formula, this is somewhat similar to the one that appears in Cohn's distance formula. Of course, it's not maybe that easily seen, but at least that's where the inspiration came from. Of course, you don't have a norm. There you have some things bounded by 1. Here you have just something negative definite. But that's about causality. That's not about the metric, so that's slightly different. But at least that's where the inspiration came from. And now you need to have at least, well, you need to have enough of the causal elements so that the span, the complex span of them, if you close it, well, that's a pre-C-star algebra or any dense C-star algebra, dense subalgebra of a C-star algebra. So if you close it, make a C-star closure, then you should get the same thing. So these guys should really span the whole algebra. And this corresponds to the fact that that you need you need enough of the causal functions to span the whole algebra. So you need a causal structure. That's how it is. Okay, and once we have that, we have the following proposition. So let C be a causal cone, and for every two states on this big algebra, we define psi to be in the future of chi, if and only if we have this inequality for every element of the causal cone. Well, as simple as that. And what we can show that it is a nice partial order relation on this space. Now, I said that I treat A as merely a technicality. Well, I do so because I will be mainly interested in pure states of my smaller algebra and my states of bigger algebra. So we have a specific procedure how you do that. Well, you basically discard states that are, in a sense, localized at infinity. So you discard, you only take states which do not have the whole algebra, the smaller algebra, in their kernel, right? And in this way, you can somehow get rid of the unitization. But there's another point also, that the unitization is there. So if you can, the partial order is also there in this bigger space. So that might have some implication of extending the causal order to boundaries of spacetime, which is actually a very old problem. And many wise people worked on that, including Penrose, Hawking, and all that. So who knows? There might be some relation, but for the moment, we just discard. Well, we treat this unitization as a technicality which we need for the definition to work, but somehow the physics will not depend on that. At least not the physics in the space-time itself. Now let's get to physics. So, okay, as I stressed, I follow mainly a bottom-up approach for the pseudo-Riemannian spectral triples. So I'm not really aiming at providing you a full list of axioms for a spectral triple pseudo-Riemannian so that I can reconstruct my manifold. Rather, I'm looking at the manifold and trying to see, okay, what kind of algebraic elements do I need to describe that without the notion of points and the usual stuff. So, of course, if I have a pseudo-Riemannian manifold, and then I take the algebra of smooth, compactly supported functions, I take the space of square integrable sections of the spinor bundle, and the usual Dirac operator, I will get a pseudo-Riemannian spectral triple. Of course, that's also the common denominator of all of the approaches to pseudo-Riemannian spectral triples. Well, you need at least that example for the things to work. Now, if you have that, and you have a causally simple spacetime, well, causally simple means slightly less than globally hyperbolic. Well, roughly you have global time, but its level sets are not necessarily Cauchy hypersurfaces. So it's just slightly less than global hyperbolicity. So if you have something causally simple, and you take the associated pseudo-Riemannian spectral triple, then, of course, if you look at the pure states of your algebra, you just recover your spacetime. And then what we have shown is that if these states are related, causally related in the sense of our definition, well, it happens if and only if the corresponding points of the spacetime are causally related on M. So we recover, yeah.
What is the meaning of causally simple?
Causally simple? You want the precise definition? Okay, good.
I don't know.
Yeah.
The idea with, I don't know, with global hyperbolic, if there are relations with the, I don't know.
Okay. Any globally hyperbolic is causally simple. Okay? So that's causally simple is a bit more. So the technical definition is that if you have J plus, which is the set of all pairs of points that are causally related, it should be a compact, closed set. That's the definition of causally simple. And well, you can show that it implies global hyperbolicity in particular. Okay, but it's slightly less. Okay, so we have the usual causality recovered. Now, what else can we do? Well, first thing we want to do is to go almost commutative and try to see if there's something new up there. So, of course, you can take tensor products as usual, and you will get an almost commutative pseudo-Riemannian spectral triple, as again is the common denominator of all of the approaches, so we're on the safe side. And now, what do I mean by an almost commutative spacetime is the following thing. So pure states of your algebra, right? And this, by the Cadison theorem, will give you just your spacetime, the usual spacetime, times some internal space, which depends on the type of the algebra you take here. Okay? So, of course, that's maybe a bit exaggerated, because spacetimes is something with a metric, and this equality, this is pure topology. It's not much more. So I won't claim that I have a metric on that, but I do have a causal structure on that. So that's metric up to a conformal factor. Okay? So at least that's my viewpoint of an almost commutative spacetime. That it's just your regular spacetime with some additional internal structure which encodes some properties of particles or whatever. Okay, and then if you want to go to truly non-commutative things, then you also should look at pure states of your non-commutative algebra, and this is what you should call your spacetime. Okay. Now, the first result that you get in this approach is that there's no Einstein causality violation in almost commutative spacetimes. And that's a general result. So you take any almost commutative pseudo-Riemannian spectral triple such that the causal cone exists, because of course it might happen that it does not exist, and then you don't have a causal structure at all. But if it exists, then if two pure states are causally related, then the corresponding points of your spacetime should be causally related also. Okay? So it means that if you move just on the spacetime, you cannot violate Einstein's causality. You can.
The finite triple here is a normal spectral triple, not a.
Yes, it's a Riemannian one.
Riemannian.
Yeah.
And that's crucial for this. Is that right?
Well, yeah. Okay, that's. I put it. So the condition is actually here. that's an important question. Okay, let me maybe address it, because you might have spotted that I might cheat a bit, because I'm always saying about pseudo-Riemannian things, whereas causality is a purely Lorentzian phenomenon. You don't have causality in other signatures, right? You don't have this. You don't have a partial order relation, just as it is. But now, so of course you would like to have some Lorentzian spectral triples. But somehow my viewpoint is that if you would try to do this causal structure on something which is not Lorentzian but something else, you will just fail. You will not get a causal cone, because probably you won't have your causal elements span the whole algebra. That's my impression. I didn't check that, but to be on the safe side, I assume that the causal cone exists. But on the other hand, as you have seen, there are in the other approaches, you can see that, for instance, in Kuhn's approach, the spectral triple, the internal spectral triple, should be Krein as well. So there's some indefinite signature going on there. And the question is whether it means that there's no causality at all, or is there something? I think that there might be. Because if you look at, for instance, the question of dimension of a spectral triple, what you learn is that if you want to describe a non-commutative space, a single number is not sufficient. You have a dimension spectrum, and it encodes much more information. You have the p-summability, but you have poles of the zeta functions which tell you more. You have, for instance, some complex poles which tells you about some self-similarity structures. You can have double poles, things like that. So it might well be that there's no good notion of a signature of a non-commutative spacetime, but there's, for instance, signature spectrum. Who knows? Well, anyway, to be on the safe side, I just assume that the causal cone exists. It certainly exists if I start with a causally simple spacetime and I take a Riemannian spectral triple. That's for sure. That's guaranteed that it exists. In other cases, who knows? Okay, anyway, so this proposition tells me that if I want to move on my spacetime component, I cannot violate Einstein's causality. I cannot move faster than light. But it doesn't tell me everything, because as I will show you, there are also constraints on the motion in this internal space, funnily enough. Okay, so, well, what's the easiest algebra, finite algebra you can even imagine? Non-trivial, say. Well, just two copies of C. That's a two-pointed space, or if you take it almost commutative, you get a two-sheeted space-time. And that's where you can formulate electrodynamics, right? So you take this as your finite algebra. You take just a natural Hilbert space representation, and you take a Dirac operator. Well, you don't have much choice there. With just a single complex parameter, let me call it M. And then if you look at the pure states, well, you can either see it as one copy of spacetime and some internal degree of freedom, which can be either 0 or 1. Or you can call it -1/2 + 1/2 if you want. Or you can look at it as just two disjoint copies of your spacetime. So here's the result. Well, that's already included in the previous theorem. If you just want to stay on one sheet, so you don't want to change in the internal space, you can do so as long as you respect Einstein's causality. But if you happen to move also up, or changing in the internal space, you can do so, but you need enough of proper time. And that's the formula. So You can move along any time-like geodesic. Of course, if it is null, then you're bad because it's 0. And if it's any time-like geodesic, its length must be at least pi over 2 modulo of m. Okay, so that's the picture. Well, it's a bit dark, but anyway. So here are the two sheets. If you start here on some point P, then you can move inside of the cone to some other point Q. You can do so along your favorite future-directed time-like curve. But if you want to jump, you can do so, but you need enough of the proper time here. And if you look at this formula, this factor 1 over modulo of m that appears here is nothing else but the cone's distance between the two sheets. Okay, so there is some relevance here. Well, the funny thing is that we are getting this pi over 2 factor, funnily enough, which seems to be important. I will show you why. Now, yep.
That means that there are two cones, one on the upper sheet, which is the usual one, and a second one, which is probably not a cone in the usual sense, but there is a portion of the lower space, which is the future of a
yes,
certain point.
yes, it is.
But this is not a cone. It's a
Yeah, well,
huh?
yeah. Well, that's the picture. Okay. That's what you wanted, probably. Okay. Yeah. So that's about mixed states. So you can consider a part of mixed states, not all of them, but only a part of mixed states. So some internal mixed states which fills the space between the two sheets, right? And then you can ask about the causal relation there, and then you discover this formula, which is a generalization of the other one. So if phi is 0, psi is 1, then you just get the pi over 2 factor. And in general, you have this kind of picture. So if you start here, you can move up, but you have to stay under this cone surface or whatever else you call it. So what?
Between there are no points. No, these are two sheets.
No, these are mixed states.
Ah, okay.
These are mixed states. So it's not. Okay. In my viewpoint, these are not points of your almost commutative spacetime. These are mixed states, but they will have some interpretation also. But that will come later. But anyway, you can, for instance, project this figure on one sheet and the other. So you will have your cone here, and then the picture on the other cone will be right along this curve. Yep. Phi? Yeah. Well, phi is well, okay. That's just phi. Phi is psi. No, well, it's not psi, but it's the same type of psi, right? It's the same variable. Right? It's between 0 and 1. Okay. All right. So now to the physics. So the question is there some physics behind it? Well, at some point I felt I rediscovered some peculiar phenomenon in relativistic quantum physics, which is called Zitterbewegung. Zitterbewegung, bad pronunciation. And that's a trembling motion of the electron. That's a funny effect discovered by Schrödinger himself in the 30s. So, okay, let me explain you the original idea. The original idea was that if you have your Dirac equation, and you just treat it as the usual Schrödinger equation, and you look at the position operator, you just take x to be your position operator. Whether it's reasonable or not, that's another story. But if you take that, and you look at the Heisenberg picture, Heisenberg evolution of this position operator, you will discover that it quivers. It quivers, and it gives your massive fermion a kind of a trembling motion. So now there was a long discussion whether it's a physical effect or not, because you need to, you can show that you need both positive and negative energies for that to happen. If you have only positive energies, that won't happen, or only negative energies, that won't happen either. But there is another viewpoint that you can adopt on that, namely the chiral viewpoint. And these are actually compatible, but it's just, mathematically it's the same thing, but on the level of, say, interpretation, that's slightly different. So if you have your massive Dirac equation, which is this, And you have your chirality eigenstates, which are left-handed and right-handed particles. So you project this on left or right-handed component. Then you discover that the master mixes the chiralities, right? So that's the picture from Penrose's book, the zigzag picture of the electron. And he says that, well, you can look at this equation in the following way. So you have a left-handed particle which moves with the speed of light, and then you have a right-handed particle which also moves at the speed of light. And this equation tells you that the right-handed particle is a source for the left-handed particle, and the contrary, right? So then what you get is this kind of a zigzag picture with time. Again, this idea was also pondered by Brout, who was actually very interested in Kahn's formulation of the standard model. And what you see here is a picture from his paper from 2001. And that's just the two-sheeted spacetime, right? So he calls one sheet right-handed, the other sheet left-handed. And here is how he would describe a motion of a massive fermion. Okay, so he stays left-handed, he jumps. That would be the picture. So that was a qualitative picture. And what seems to be happening with our formulation of causality is that we can get to a quantitative picture. Because if you compute the time of Zitterbewegung, so the period of Zitterbewegung in electron's rest frame, you discover this number. Does it sound familiar? Well, it's just this one, up to a factor 2. But this is, of course, the time from jumping from one sheet to another. And that's the full period. So that's exactly it. That is the same number. So that would be our picture. If you're a massive fermion and you want to move, if you have zero momentum, then you will move like that along this curve. And if you happen to have a non-zero momentum, you will move along this blue curve. But you still move on the boundary of the cone, but the cone in this extended space. So the picture that emerges is that a massive fermion is like a photon, but in two-sheeted spacetime. Okay, now that all seems very nice, but of course, this is a classical picture, to be sure. Because as I told you, well, all of the things that we do in almost commutative geometry, these are classical things, right? Cannot claim it to be anything quantum. Well, it's still funny that you can get the same kind of effect, which here it's explicitly quantum. Here it's just classical motion, nothing more. What is quantized in this picture is, in a sense, this internal state. Because the interpretation of this state that is here in between, well, it's a mixed state, so it tells you that you have a certain probability of finding your particle in a left-handed state or in a right-handed state. It's not that the electron moves in some funny space, it's just its probability changes, right, in time. And if you measure it at some point, well, you will get the statistics according to this evolution, okay? Okay, so, but anyway, this is a would-be picture for a classical fermion. Well, these unfortunately do not exist in nature. So the question is, can we do more? Can we somehow confirm this picture? But okay, well, before we do that, let me say that we can do better than that, because we can add fluctuations of the Dirac operator. So you can add a gauge field, well, an electromagnetic gauge field, and a scalar field. Well, again, I don't care whether they come from first-order condition or whatever things. This is the things I can add, okay? So if you write the action, the fermionic action, that's what you will get. And that's, again, the picture from Penrose's book. And he says that, well, okay, the mass term is actually the interaction with the Higgs field. So that would be the diagram you should consider in your quantum fields if you want. What we can do, we can still get the causal structure. And here's just the pure state case, so jumping from one sheet to another. And what we see is that our formula gets modified by the presence of this scalar field. Okay, so we have this funny Higgs field or scalar field, entering into the formula, which is just, if you take this to be constant, you just get the usual formula for the proper time along a curve. Now, if you have this thing, the mass depends on your point of space-time, you have to put it under the integral. So in fact, it acts as a conformal factor, because you can reinterpret this as a propagation in the conformally rescaled space-time, right? Because this one, you put it here, and you put it into the metric. So that's how you can look at it. So also a striking thing is that there's no impact of the electromagnetic field on this formula. Well, that's simple, because it's abelian, so it commutes with this perturbation commutes with your algebra, okay? So it won't have an impact on the causal cone. But on the other hand, this scalar field does affect the causal structure, does affect this formula, and it acts as a conformal factor. And also, we are always on the curved spacetime. So that's far more general than the usual, say, considerations about Zitterbewegung. But still, this is classical. So, and what we would like at the end is to measure something, to see that, okay, I give you an inequality, and now I want to invent an experiment saying that, okay, let's do the experiment. So that's an inequality. Either it is right or it is wrong. There's no freedom. It's not a prediction of mass that you can maybe adjust a little bit. No, it's just an inequality. Okay, either it is satisfied or not. So to do so, one strategy we adopted is to go to full mixed states. These would be Borel probability measures. Okay, so that's a work we did with Tomek Miller. Namely, if you just take your commutative algebra, then your states will be probability measures on your space-time. So you have beasts like that. You have your space-time here, and then you have something which is smeared. It can be smeared around on the whole space-time, right? And then you can ask the question: when does one probability measure causally precedes another? And we found some very nice picture of what is actually happening. So, well, you can think of it intuitively is that if you have densities, then each parcel of the probability density should move along a future-directed causal curve. But these parcels can also split, and it's like a causal probability flow, right? So that would be the picture. Okay, that's, of course, a telegraphic shortcut of everything we did, but just 2 comments. So again, we find a very nice link with optimal transport theory, but now it's an optimal transport theory in Lorentzian context, which is not very much explored. I would say that almost not explored at all. And okay, one point is that for this thing, we don't need the Dirac operator, actually. We only use something we call causal functions. So causal functions are functions which are non-decreasing along every future-directed causal curve. So it's similar in the spirit to a time function. Okay. Well, anyway, we don't need non-commutative geometry to do that. We just need classical things. But now what we would like to do, because if you look at it, well, you think that, well, maybe there is some quantum flavor behind it, because quantum objects, after all, they are just the things that you cannot localize. But they are smeared over the whole space, and maybe even space-time if they come from some quantum fields. Who knows? So anyway, one of the applications of the work we did with Tomek is to try to apply it in the wave packet formalism. So now we stay on Minkowski space-time. So you have your Schrödinger equation with your favorite Hamiltonian, and then you can observe that your wave function gives rise to a family of measures on M. So at each point, so at each time instant, you have a probability measure, which is defined just like that. Okay, have the norm square of this wave function, and then you take a product with the delta function in the time coordinate, and that's it. That's your measure. Okay, so these will be measures which are localized on time slices, right? And then you look at their evolution, which is implied by the evolution of the wave functions. You get a nonlinear evolution of the probability measures, and you can ask whether this guy is causal or not, in the sense of just this definition. Okay, and that seems not to be an unreasonable question. Let me also stress here that we do not assume, for instance, well, we just take the viewpoint that any wave function defines a probability measure. That's it, full stop. We don't say that that's a probability of the actual probability of finding your particle, because for that you would need to assume that there exists a position operator, which is a tricky business in relativistic quantum theory. Here we just say that, well, we have a probability measure, so why not looking at it, right? So what we discover, for instance, is that the Dirac equation yields a causal evolution. So if you rewrite your Dirac equation as a Schrödinger equation, which you can do, then your evolution will be causal in the sense of this definition. And mind you, it will be causal whatever initial take you take. Localized, smeared, positive energy, mixed energy, whatever, it will always stay causal. But this is not the generic case. If you take another Hamiltonian, for instance this one, which is also a nice relativistic Hamiltonian, you discover that the evolution is not causal in the sense of this definition. And this is actually in accord with some other results from quantum theory, like Hegerfeld theorem and things like that. So that seems to make sense. Now, if we want to get something more out of our correspondence with Zitterbewegung and two-sheeted spacetime, we might look into the full mixed state space of the two-sheeted spacetime, which will be the probability measures on the two copies of M. So that's one picture you can draw. So we have a probability density, which is this guy here, and it is localized on a hypersurface between the sheets. Okay, so that's one of the options. Or you can look at it that you have two densities, one on one sheet, the other on the other. They are not normalized to one, each one of them, but if you add them, you get something which is a probability measure. So it's normalized to one. These are two pictures. And let me stress that the causal structure on this beast is not the same as the one of the bigger space on M0, 1. Well, roughly because you have less causal functions. But somehow the picture that we get, and that also appeared in Pierre's thesis, that you can actually reinterpret the distances on two sheets in terms of just a metric in a higher dimensional thing. This picture breaks whenever you go to mixed states, because your algebra is different. Anyway, if you get now back to the Dirac equation, well, you can see again that if I have an arbitrary solution of the Dirac equation, it has a left-handed component and a right-handed component, which are orthogonal to each other. So you exactly get this picture. You have a probability measure, which you can always split into two parts, the left-handed and the right-handed. So it seems to be corresponding nicely with the thing we get here. So now that's an ongoing work. Here's the conjecture. I conjecture that the Dirac equation respects causality not only on a single sheet, but also in the two-sheeted spacetime. And now what that would mean? That would mean that given any initial state, I can write an inequality that should be satisfied. And this inequality is something you can measure experimentally. Right? As long as you have Dirac spinors. Now, there are two problems here. First problem is that if you compute this Zitterbewegung time for a free electron, it's of this order, 10 to minus 21. So that's 3 times slower than anything you can do in any experiment. The best they can do is attoseconds. Okay, so it seems that we're far from being able to measure anything like that. Second point is that the true electron requires a quantum field theory description, which is beyond this picture, of course, because I'm using wave packet formalism, and this is something that breaks it. But there is something called a quantum simulation, which is very popular these days. And the idea of a quantum simulation is that if you have a quantum system, which you cannot measure for some reasons in nature, like, for instance, Dirac particles, because you know that they require a quantum field theory description and so on, but still you have a nice Schrödinger equation. You can find an analog system, for instance, using trapped ions or Bose-Einstein condensate or photonics. And you can you can write down the evolutions there, and then you discover that you get the same Hamiltonian, you get the same dynamics. So you can simulate the system that you want. You can, for instance, simulate Dirac particles in a tabletop experiment. And this has been done, at least in 3 experiments that I know of. That's the one about Bose-Einstein condensate. So well, you have some levels of the atoms, and you write the dynamics, and then you discover that, well, that's just the 2-dimensional Dirac equation. And then you can measure here they measured this position operator, which is supposed to quiver in the Dirac particles, and that's it. It indeed quivers. That's what they measured, right? Okay. Of course, it does not mean that the true electron will undergo this kind of things, but it means that this kind of systems is available to you, and it is available in a tabletop experiment. So our idea is that once we get to the inequality, and I'm sure that we will get to the inequality, we actually do have an upper bound and we have a lower bound. So they just have to meet. And here it is, our inequality. If we get there, then we can predict not only qualitatively the idea of Zitterbewegung, but quantitatively we can predict these periods, and we can predict also how it changes when you change the mass. And then you can do whatever you want. You can change your mass for a scalar field. You can add electromagnetic interaction and see that it does not change. So there seems to be a room for some nice physics in there. Okay.
I didn't quite follow it. So the thing on the right was a BC. But what is the thing on the, what is the graph on the right show?
Well, that's the Bose-Einstein condensate, and that's from the trapped ion experiment. Yeah. But they are.
What they're showing there, data points. What are the curves?
Well, so this is the because as I told you that's one of the interpretation of Zitterbewegung is the dependence of the position operator in time. So it should quiver whenever you have a non-zero mass, and that's what they're seeing here. Because in this kind of experiment, you can, well, you can measure the you can measure the modulus square of the wave function explicitly. Okay, so that's what you can measure. And it's independent of the fact whether it makes sense for a true electron or not. That's an analogous system which undergoes the same dynamics. Yes.
So Dirac equation has this kind of solutions.
Yes.
Simulated.
Yes. Yes, true. But yeah, in this sense, it's just, well, these experiments were just the, say, proof of principle experiments. It says that you can simulate Dirac equation. But what I'm saying is that if there's something more behind Dirac equation, like kind of inequality that needs to be satisfied, that is something you can measure in these experiments, right? That's my claim. Okay. Well, it's just the other mass. Okay, so that's for a big mass and that's for a small mass, and you see that if your mass goes to 0, then drops out, right? Okay.
There's one other thing which is that in graphene people find that the phonons.
Yeah, graphene is also one of the media where you can use this idea of a quantum simulation. Okay, let me pass to the conclusions, and let me explain myself from this somewhat pompous title. Well, what I showed you is that there is a non-trivial Lorentzian geometry of the two-sheeted spacetime. So abelian gauge field does not affect it, but the Higgs field does. Now, if this is the good picture, then that would be the tip of the iceberg. Because then, well, you can look at C plus H, but there's not much difference because that's a real algebra. It has also only one state, so that would be the same. But there is much more. You can, for instance, just take C plus C and study neutrino mixing. You have three states of your particle. You can take M2C and you can look into Heisenberg model for pions or kaon systems. Again, things that exist in nature. You can take M3C and study some color change dynamics. So also the point that I want to stress here is that I do not like to focus too much on the fact that we have our particle physics models very, very restricted. I don't think that's good because, for instance, this spectral triple, that's not an even spectral triple. But so what? Heisenberg model for pions is not a chiral theory. But still, I want to describe it with my spectral triple approach. So that's why I'm not focusing on the reality structure. Well, it's just, it's there or it is not there. Okay, let me skip that. Another point that I want to make is that, okay, there is the problem of quantization, spectral triples, quantizing the fields. Now, what do you usually do? Well, what you always do in any quantum field theory, you need to impose a kind of micro-causality condition. So either you impose it, either you check it, but it should be there. So your observables related to the space-like separated region, they should commute, or anti-commute if it's fermionic. Now, what emerges from this picture is that if you have a two-sheeted space-time, you have a different causal structure there. So you can interpret it again as a one space-time with two fields. So should we have, for instance, something like that you have two fields, a left-handed and a right-handed, which do commute or anti-commute whenever we have this extended causal relation satisfied or not? Well, that's an idea. That's a hint. Well, I don't know much about quantum field theory. Maybe some of you can tell me that it is reasonable or it is not reasonable. But I think that's something one has to look at. If we treat this picture of space-time seriously, and you want to do quantum field theory, well, you need to take into account the causal structure, right? So take-home messages. There will be 4, apart from the Banach-Simons semester, of course. That's the essential one. So the Lorentzian version of NCG is needed. I mean, you have seen that already in the Adir's talk. You will see more of that. So I'm happy that it gained some momentum, and there are people working on it. But my viewpoint is that if you want to understand physics, you need to look at the Lorentzian aspect, because our world is Lorentzian. That's how it is. Now, Kahn's distance formula may actually have some empirical consequences, because it appears there in our causal structure. Probably you can do more. Probably you can define a Lorentzian metric there, and then you get the full dynamics. So that's it, and that depends on this Kahn structure. So it really deserves more attention. Now, how about quantum field theory? Maybe it needs rethinking. If you have some non-trivial causal structure, maybe you need to construct your quantum fields in a different way. I don't know. And then the last message is that physics is much more than just gauge fields. And that's something I stress, that you need other models, but that's also good that you can look at quantum simulation, for instance. So why not looking for applications in solid-state physics, atomic physics, whatever else? Try to use the spectral triple machinery there. It's much easier to check, isn't it? Okay, thank you very much. Mm-hmm. Yes.
If it was the opposite, it wouldn't be good.
Mm-hmm. Yeah, that seems to be happening, yeah.
I have a question. Sorry. Go ahead.
Just, there were some attempts to build Lorentzian or in any case spectral triples, but even from Franco, as far as I remember. But there was a problem with this condition, some conditions imposing a kind of commutative time. I mean, imposing conditions on the C-star algebra, in some sense.
Yeah.
And is there some problem like this in this case? Or
Well,
just completely general?
No, I must say that I not completely agree with Nicolas' viewpoint, because his viewpoint is more into the reconstruction theorem. So he says that, okay, I want really to reconstruct, to get back my space-time from where I started, from the algebraic viewpoint. And if you want to do so, you get into more and more restrictions, and then, for instance, you need to impose kind of commutative time assumption or whatever. But my viewpoint is that well, maybe you don't need that. I mean, after all, you are just following a bottom-up approach, right? So one result that is worth mentioning is a result by Nicolas and Jean-Christophe Wallet. They computed the causal structure on YL plane, and without the assumption of any commutativity of time or something like that. And you do get a causal structure for coherent states. And it's actually, again, it's coherent with your results on spectral distances on YL plane. So it seems that you don't need this assumption. I mean, your time is not there. Your time is, if there is any time, it will be in the space of states. That's my viewpoint.
In any case, with this generality, you didn't touch the subject of recovering the space-time. I mean, what should the difficulties be in this case?
Well, it depends how badly you want to reconstruct your manifold. I mean, if you're after a generalization of Kahn's reconstruction theorem, then, well, I think it might cost a lifetime of not only one person. So I think it's important at some point to see what's going on and to get these differential structures and the indefinite metrics and so on. But I think we are quite far from it. Yeah.
Okay, I use the Chaiman privilege for final question, which is really a comment. When the Zitterbewegung are a consequence of the fact that you are doing relativistic quantum mechanics with only a particle relativistic quantum mechanics, they disappear in quantum field theory because of they are substituted by the fluctuation of the vacuum, the creation of pairs. So if you are forcing your theory to have just one particle and you are following that particle, the theory is crying for antiparticles.
Yep.
It's the same as the Klein paradox of the barrier, that you have a flux which is paradoxically. So basically, so is there if you were to do really a quantization, a quantum field theory quantization of your theory, will these fluctuations disappear and be substituted by what? You have to put the antiparticles in the game.
Maybe, okay, so
the chiral structure.
Yeah, so two comments here. So firstly, I don't know how to do quantum theory. I just gave you my idea, but I have no idea whether it will work out and what comes out of it. Whether Zitterbewegung is present at the quantum field theory or not, that's a debatable question. So if you have only positive energies, then nothing quivers. But as you said, you have vacuum and you have virtual pairs. So you do have some contributions from negative. Yes.
Not Zitterbewegung, are the creation pairs of the electron, which is radiating photons, and the photons are creating pairs. So there is, of course, there is a very fluctuating structure around any electron.
Yeah, but you don't need photons for that.
It's the cloud of matter and antimatter. So basically, relativistic quantum mechanics is an inconsistent theory. That's all. It's good to learn it, but I don't teach it anymore.
Well,
but the course is short, so my students don't know what that Zitterbewegung and the Klein paradox are, because I immediately go to quantum field theory.
Well, okay, so 2 points. First point is that you can, for instance, consider four-sheeted spacetime, right? Where you have the reality structure. That's what you probably need. Yeah. And then if you write your Dirac operator, you discover that you have this 1/m distance between, say, 1, 2, and 3, 4. But between the others, the distance is infinite.
Yes.
So it means that you cannot change from particle to an antiparticle, which still might be consistent. Yeah. Okay. So my point was that I don't want to force my theory. That's the theory who forces me. It forced me to look into the atomic physics because I know that.
Your work is very nice, but there can be developments if one tries to make also some look into Torus quantization. So you did a very important first step of relativistic quantum mechanics. So
I claim that quantum field theory is important. Maybe we get something new out of it. I don't know.
Okay, Latham.
I was just going to ask. I mean, so
Mm-hmm.
Do you think is the step to going to the case where both are non-commutative, is that related to the question of how to quantize? I mean, one issue is whether that's the
Well,
same
that's
as guys. I mean,
well, that's another question. I think that, well, probably there are two approaches. One approach will tell you that you can do quantum field theory within spectral triple approach. Maybe you can, maybe you cannot. No one did, but the others would claim that no, it's not sufficient. You need to just have something external, like do quantum field theory on spectral triples. So if you are able to express a quantum field theory within spectral triple language, then we should have some kind of causal relation there and something of this kind. But how can you do that? I have no idea. But an important thing is that whenever your algebra becomes non-commutative, and that's an important point, then your states are no longer separable, which means that you have a kind of entanglement between the space-time component and the matter component, which is physically very, very appealing. And it might have consequences, for instance, for the horizon problem.
well, I was going to say, is that, I mean, in ordinary quantum mechanics, that exactly is where quantum phenomena arise. That's what I mean. That's the
Mhm.
geometrical picture of what's happening in quantum. In other words, could it be that if you just went to the maybe could you say again what is the main technical obstruction to going to the case where the whole algebra is where both where the whole algebra is non-commutative? Is it?
Well, I think that the problem is not technical.
Please.
Yeah, okay, just finish that. I think that the problem is not technical, it's conceptual. Which algebra you take? I mean, what's your spectral triple for a quantum field theory? If there is one at all. So once you have it and you can check the axioms, or at least some of them, off you go.
Okay, off we go for lunch.